So, if there's anybody in the room who missed the lecture yesterday, one of the important things to know about this course is that the lectures are in fact recorded. So if you hop onto the YouTube channel that's listed in the syllabus, you'll be able to get an archive of not only this offering of this course, but previous offerings of this course as well, if you're interested in, like, skipping ahead in the course, out of personal interest or any other number of factors. So that is a resource. Please use it. I highly encourage you to watch the lectures back at, like, at least 1.5 times speed, because, it's just long, And you can't speed me up now, but at least you can do that when I'm recorded, But anyway, so, let me think. Do we have any announcements? We're still working on sorting out the tutorials and the Jupyter system for this semester. We still, believe it or not, the Jupyter system that we're using this semester was also, the same server was used for last semester, and, we were madly scrambling yesterday to get the final grades in because, they had their exam, last Thursday, so it's been a bit of a crunch to get everything in for the deadline for the submission of grades, which was yesterday, So we're still in the process of sorting out the computer system. Don't worry, we'll make an announcement when it's ready for you guys to try to log in. Yeah? Awesome. So, we left off. We were just about to get into some miscellaneous information on programs, which is not really direct programming knowledge. I'll try to get through this reasonably quickly so that we can get on to the main topic for today, which is more directly related to how to actually program. We haven't posted the assignments yet, but basically by the end of this lecture session today, you should be clear, you should have enough information presented to you to be able to try some simple programming problems yourself as practice and in anticipation of the assignments which are coming up next week. So, and I'll direct you to the problem set that I highly recommend, which is not for marks, but for your own personal edification. They'll also go through a couple of the problems in tutorial next week. So, good. Do we have any questions before we start off today? Good. Awesome. So, the thing that we stopped off at last time, the organization of the computer. This is what's known as von Neumann architecture. It's not completely essential to understand computer architecture in order to be able to program a computer. Otherwise, very few people would actually be able to program computers because computer architecture is very, very complicated. However, it is informative to go over a few of the sort of broad strokes. So, a computer is a machine which receives input and calculates output. Input may come from any of a number of different devices, right? Standard ideas of input are your keyboard and your mouse. You can also think of incoming network packets as being inputs to your device as well, if you want to extend this idea to the internet. Generally speaking, we won't talk about the internet very much in this class just because it's a very complicated thing and we're just trying to learn the basics. Output devices can include things like monitors and printers and output packets sent back out over the network. Within the context of the computer itself, the memory unit, which stores data inside of the computer, can also be considered both input and output with respect to the programs that you're trying to run. last time we reviewed the different types of memory that exist inside of the computer. To recap those quickly, you have random access memory, aka your hard disk. This is your permanent memory storage and the location where your files are stored. It's permanent memory that survives the power cycling of your device, right? So any memory that sticks around once the device has been turned off and then back on again has been stored in what we call permanent memory, and that's typically called ROM. Random access memory is the next step up from that, at least stepping closer to the CPU. RAM is volatile, which means that it does not survive power cycling. It requires a constant power supply in order to hold values. So you might say, why even use it if it's this impermanent? It's much, much faster than your random access memory, typically speaking. In fact, not even typically speaking. In all cases, RAM is faster than ROM. You have a couple of tiers of memory that get increasingly volatile and increasingly fast the closer you get to the CPU, culminating in what's called register memory. Register memory is the memory that is contained within the CPU itself. It is the only memory that the CPU can directly operate on. The CPU can only perform, for example, arithmetic operations on register memory in order to be able to perform any calculations on memory that's in one of the exterior memory units. It must be loaded from the exterior memory into register memory, then operated on. So if you were to break a Python program down in terms of the simplest operations that the computer performs, i.e. break it down at the level of an assembly language, there are quite a lot of load and store operations that are implicit in everything that you do. One of the great innovations of the types of programming languages that most people use is to hide all of these memory interactions from the user so you don't have to worry about it. So, a couple of trade-offs. Trade-off number one. The more volatile memory is, the faster it can be accessed, right? The memory that's contained in the CPU itself actually degrades over time. However, it's refreshed sufficiently quickly that this sort of slow decay over time doesn't actually impact the holding of values, although it can sometimes. Computers are not perfect machines. So that's trade-off number one. And I forgot what trade-off number two was. All right, let's keep moving. So, CPUs and machine language. CPUs operate on bits, that is zeros and ones. Bit is a very, very important term if you haven't heard it already. Bits are grouped into words, all right? Anybody know how big a byte is? B-Y-T-E? Yes?
8 bits?
8 bits, yes. So, byte, like your smallest useful grouping of bits is going to be a byte, right? So, 8 bits constitute one 1 byte. You distinguish that from the word size of the operating system. And I know I'm throwing a lot of terminology at you, but this is kind of like, that's welcome to lectures, I guess. So, as computers have become increasingly complex over time, one of the ways in which computers have become more complex is to support more bits at one time, right? So, I always like to talk about Nintendo at this point. How many people are aware of the different Nintendo consoles? A couple of people. All right. A little bit. All right. So, back in the 80s, Nintendo develops the Nintendo Entertainment System, or the Famicom, depending on what region you're in, right? this was an 8-bit system. The word size of the operating system was 8 bits. This meant that the arithmetic operations that could be performed were limited to numbers that were 8 bits in size. Now, the number of bits that are used to represent a number limit the number of numbers you can represent, basically. So the way that the binary code works, right? If you have, I'm just going to use 4 bits, right? 4 zeros is equal to 0, right? 3 zeros and a 1 is equal to 1. 0, 0, 1, 0 is equal to 2 in the decimal system, right? So this is decimal, this is binary, right? 0, 0, 1, 1 is equal to 3, etc. This is how things count in binary, right? There's a mathematical equation that you can use for this. It's 2 to the power of this guy, 2 to the power of this guy times whatever this is, 2 to the power of 1 times whatever this is, 2 to the power of 2 times whatever this is, 2 to the power of 3 times whatever that is, right? This is the same way that the decimal system works. If you have a number like 2,347, what that actually is it's 7 times 10 to the 0 plus 4 times 10 to the 1 plus 3 times 10 to the 2 plus 2 times 10 to the 3, right? The same system, it's the same thing in the binary system. The reason that the binary system works is, of course, you can represent these 1s and 0s as high and low voltages, which means that you can design electronics to be able to do math with these high and low voltages. But this is essentially, this is the binary system, roughly introduced. So, using this type of mathematics, the largest number that you can represent here, you can go from 0 to 7, right? Each additional bit that you add to the representation doubles the number of numbers that can be represented, right? In the same way that each time you add a digit to a decimal number, you increase the range of that number by a factor of 10, right? So, one of the things that, has been one of the things that we want to do is we want to increase the number of bits that we're using to represent numbers, sort of historically speaking, so that we can represent more and more useful things or things with more and more fine grain, right? With a greater level of granularity, shall we say. So anyway, so the Nintendo Entertainment System operated on 8 bits, right? The Super Nintendo operated on 16 bits. Now this had lots and lots of different effects. With the Nintendo Entertainment System, you could only represent 255 colors, for instance, because 255 happens to be the maximum number of numbers that can be represented with 8-bit math, right? Now, if you take a look at the Super Nintendo versus the regular Nintendo, you can represent a very, very large number of colors. And one of the things that they did with the Super Nintendo at the beginning was just, oh, look at all these colors that we can do. It's amazing. We can do like soft gradients between 2 different colors. It's amazing. And it was enabled by 16-bit mathematics. So, when you design a CPU, there is a certain number of bits that all of the operations have been designed for. This is known as the word size of the computer, or the word size of the operating system. So, in the modern context, pretty much every CPU that you will encounter in a dedicated computing device will be a 64-bit operating system. This has been the case for quite a while. I don't anticipate them moving up to 128 bits anytime soon, because 64 bits seems to be good enough for most purposes. The more bits you put in, that has the effect of making the CPU exponentially more complex, right? So, like, there is kind of a, you could make a 128-bit operating system, but you would be like making it so large and expensive that it wouldn't be useful for consumer purposes, certainly. And we're kind of to the point with it where 64 bits is good enough for most purposes. Like there's a trade-off there as well. So yeah. So when we say word size, we're talking about the number of bits which constitute sort of the basic number of the operating system, right? Now this can vary. There are certain applications that are still using 32-bit arithmetic. For example, lighter weight operating systems like cellular telephones, some of those things are still using 32 bits because not only do you multiply the size of the chip when you're doing 64 versus 32, you also multiply the power consumption. Power consumption is actually directly correlated to the area or the amount of circuit that's involved. So, 32-bit operating systems consume less power. If your device is being run on a battery, you want less power consumption, right? Anyway, CPUs contain their very own limited memory called registers. Main operations are to load data into a register, perform arithmetic on data that is in registers, store data from registers to memory, and to jump to other instructions in your program. All of the control flow constructs that we discussed last time in class, if statements, while loops, you can break these down in terms of jump instructions in assembly language. We're not going to study assembly language in anything like any degree of detail, but essentially, the way it works inside the computer is you'll have a series of instructions, right? These instructions will have sort of an implicit labeling based on their placement in memory. So you have, the program start, right? This will be program start +0, +1, +2, +3, etc., right? You can have an instruction in here that says, like, jump to 2. So you jump at that point, you can jump back to instruction 2 and continue executing, right? It gets a lot more complicated than this, but that's kind of like the basic flavor of what a branch instruction in assembly code does and looks like. Inside of your CPU, one of the registers keeps track of where you are in the program. It's called the program counter. An operation which changes the value in the program counter we call control flow, or a control flow operation, because you're controlling the flow of the program. Make sense? Any questions so far? Cool. Good. So, programming languages. Programming languages have seen a heck of a lot of development over the last, say, 80 years. It's really not useful to talk about programming languages prior to the 1950s. The original programming languages were programmed on what are called punch cards. So you would have a physical stack of cards. You would program a program by punching holes in that card. You would then put those cards in a stack feed it into a slot in a machine, right, it would use either some kind of physical detector that would like fall through the hole, or possibly like an optical detector to see where a hole was and where a hole wasn't, and it would use that to to decode these as instructions. This is Fortran. So Fortran is a very early programming language. Stands for formula translation, one of the first. This is an if statement in a Fortran punch card. So this was prior to the storage of the program in the same medium as the data for the program. Once we developed the ability to store the program inside of the computer itself electronically, we began to be able to type out words in a computer, right? Have those words decoded as instructions, have those instructions executed by the computer, right? This required, you know, wiring up electric typewriters to the bloody mess, and, you know, having some kind, like the original, the outputs from computers in these types of, like in this era were like ticker tapes, you know, like you would have it like make out a series of dots on a piece of paper that was coming out of the computer, you know. You wouldn't have a monitor. Monitors weren't developed until later. But anyway, so in this era, you develop the sort of linguistic, quote-unquote, programming language. A programming language which is composed of, you know, string characters, things you would type out on a keyboard. For any real programming work, this remains the dominant way of programming. It's essentially the optimization point between the expressivity of the language and the speed with which you can enter it. There are other programming languages that perhaps some of you in this class have used before, which are known as graphical programming languages. Like, I always forget the name of it, but there's like one where it's got puzzle pieces, and you have to like click and drag the puzzle pieces together. It's Scratch, I think it's called Scratch. But, so that's fine for like teaching kids how to program, right? Because it sort of emphasizes and reinforces the concepts. But no real programmer would ever use anything like Scratch to do any kind of real work. You know, because you just can't work with it fast enough, right? So yeah. Not to mention, you know, it requires too much infrastructure, basically. One of the things, like if you're trying to write an efficient program, you want to like have that program running inside of a minimal client, because any resources that are used by the client of that program are also going to, like, that's just going to add to you know, the amount of resources that your program requires. Anyway, so compilers. Compilers are a very, very important concept in computing. It is not sufficient for you to simply write a program. And I just want to put it out there right now. There is this horrible misconception going around right now that I would like to correct in all of you right now. When you write code in a file, it is not called a code, it is called a program. Okay? If I hear any of you calling it a code, I'm going to correct you. So anyway, a compiler is a program which decodes another program in terms of assembly level operations. Now this is slightly different. Assembly code itself is slightly different from the machine code that a compiler will actually translate your program into, because this is still written in text, right? The machine language itself will be written in binary, right? You will have a binary code representing each one of these operations. You will have binary codes representing which registers are being used in the operation, all of that kind of stuff. It'll be coded in binary in a way that's directly interpretable to the CPU itself. But for the purposes of reading it as a human, this is what assembly code looks like. There's a one-to-one mapping between this code here and what is actually executed by the CPU itself. So, the compiler, basically, in order to be able to write any program in any language, you have to be able to download, install, and execute the compiler on your program. And this can be, this can be a little tricky because, often compilers expect you to know how to use a command line interface and stuff like that. If you're in Windows, it expects you to know a little bit of how to use DOS, unless you're using some kind of client. But anyway, incidentally, the Python compiler is not actually a compiler at all. It's what we call an interpreter. So here's the difference, right? A compiler takes in a program, converts it to machine code, which can be directly executed, and then it stops. The compiler stops. It's like, here's the executable file. You can execute this whenever you want, right? That's a compiler. The compiler takes in a program and produces executable code. An interpreter takes in a program and executes it directly. So the way that the Python interpreter works is it reads in your Python program one line at a time, converts each of those lines to machine code, and executes them immediately. So it's a bit of, like, you might consider it a bit of a pedantic difference, but it does have impacts, for example, on efficiency. Python is not an efficient programming language relative to most programming languages. And one of the reasons for that is that anytime you run a Python program, you must be running the interpreter at the same time, right? It's a big program that consumes resources. I remember there was a former student of mine, who told me once that for a project, they re-implemented some vision, it was a program related to computer vision. So, like, basically how you can take an image file and interpret it in terms of, well, that's a cat or something like that. Anyway, there are these sets of standard libraries for vision processing. And so this person took one of these library files, which is, libraries are just programs that you load that other people wrote, basically. Took one of these libraries, written in Python, rewrote it in C++, 4 times speed increase. It was 4 times faster. And they didn't change the code at all. All they did was rewrite the same code in Python syntax 4 times the speed. And it's because of the dang interpreter. Now, the interpreter, like, it's not completely useless. It is doing things like checking the validity of your program on the fly, But compilers also do that, They just do it up front. Anyway. Also, if you're using a compiler, you only have to compile it once, but you can execute it many times, whereas an interpreter must be run each time the program is run. Anyway, so, if we take a simple statement, such as u is equal to u minus v, and we were to interpret that in terms of machine language, this is kind of, so there's a term that you'll hear computer science professors use, pseudo code. It's like, this is like a real program, but it's got elements that wouldn't compile, right? So it's not exactly a real program. This is not exactly a real program because u doesn't mean anything in this context, right? But except that it's making reference to this formula up here. But anyway, so in machine language, you would load the value of u into R1, load the value of v into R2, subtract R2 from R1, store the results in R1, and then store R1 back in U. All four of these operations are implicit in this operation here. And in fact, a few more as well. Excuse me, because this is, again, this is close to, but not exactly the way the computer would actually interpret this. Any questions so far? So, I've talked a lot about programming languages. Let's examine some of the differences between them. I will reiterate my point from last class. The correct way to view programming languages is as tools for solving problems, right? Each language has its individual strengths and weaknesses. And we're about to go through some of these strengths and weaknesses. There are a couple of sort of broad categorizations you can make of programming languages that give you certain trade-offs. So you should always pick a language that corresponds to the trade-off that you want to make. So, first metric of programming languages, level of abstraction. What do I mean by abstraction? Roughly speaking, how many lines of machine code can be derived from each line of the source language? The more operations, CPU operations, you can pack into a single statement in the source language, the more expressive that language is, the more highly abstract it is. So, you'll hear me talk about mechanisms of abstraction quite a bit in this class. Abstraction is a very, very important concept in computing. So, along the dimension of abstraction, we recognize two poles, high-level languages and low-level languages. When we say high-level, we mean high level of abstraction. When we say low-level, we mean low level of abstraction. The lowest level of abstraction is the machine code itself, which runs directly on the CPU. The next level above that is assembly language, right? There are certain low-level languages, such as C, which are, roughly speaking, very loose, like they're, if you know what to look for, you can see the machine code. You can see the direct translation to assembly. A low-level language like C does not provide many ways of representing large programs. C programs tend to be small, and they tend to be fairly directly related to the underlying assembly code. Contrast that to high-level languages such as Python, R, and Haskell. In these languages, you can accomplish a lot of tasks with very little code. This makes them, generally speaking, much easier to work with, unless we're talking about Haskell. Ha ha ha! Dunking on Haskell. Actually, just so you guys know, I actually wrote my my PhD thesis work in Haskell, so I do rather like the language. Haskell, in my opinion, is the beautiful music of the universe itself, but it's sufficiently mathematical to dissuade most people from attempting to learn it. We'll stick to Python, let's say. Anyone in 1JC3 will testify to that one, I'm sure. But anyway, so with these high-level languages, you can accomplish quite a lot with very little actual work on your part. So the question is, why on earth would you ever use a low-level language? What's the trade-off here? Speed and efficiency. With high-level languages, the way that it becomes a high-level language is the compiler or interpreter itself encodes design decisions about how the program is to be run on the CPU, right? So Python has a very particular way of running itself, right? Yeah. The thing about programming and compiling, an intelligent human being can always beat a compiler in terms of efficiency. By choosing to program in a lower level language, you are choosing less support from the compiler or interpreter. That gives you greater and more direct access to the direct operations of the CPU itself. This means that you can program much more efficiently in C than you can program in practically any other language. C is the highest level language that has comparable, shall we say, a comparable level of optimization to assembly language itself. But assembly language, you can get the best optimizations possible on a computer by programming directly in assembly. So, for many applications, you don't need that level of optimization, right? The level of optimization that is useful to a program is directly correlated to how often that code is run. So the types of things that you want to code in low-level languages are operations which are performed extremely frequently. This is not going to be any code that you guys write. This will normally be reserved for the operating system itself, right? The operating system supports every program that's being run on the computer at the time. It has many, many very basic operations. Those operations will be written in either C or assembly and optimized, like basically, you know, the project of the last 50 years has been optimizing the shit out of operating systems so that, you know, they use as few resources as possible. And that work is done in low-level languages. Any questions about that? Good. So, in addition, our next dimension of comparison, application-specific versus general-purpose programming languages. So, this is where the right tool for the job really becomes very important, right? Some programming languages are designed specifically for certain applications. There are some languages that are designed simply to do statistics. There are some languages designed simply to manage databases. There are some that create web pages. Incidentally, HTML is not a programming language. It is a document creation tool, not a programming language. So if you say on your resume, I know programming because I know some HTML, you're lying, just so you know. So these types of languages, it's like very, very specific tool, right? It does one thing and it does it extremely well. Often with these types of tools, you can get them to do more general purpose things, but it's usually you want to keep them very close to their intended domain of application. There are some things that you get in here, like, for example, hardware description languages as well, which you can use a hardware description language to design electronic circuitry itself, which never gets executed on the CPU. It gets printed as a circuit board. So that's extremely application specific. In contrast to that, you have quote-unquote general-purpose programming languages. A general-purpose programming language can do pretty much anything that an application-specific language can do. The question is how quickly, how efficiently, and with how much hassle on your part. Like, you know, for example, the R compiler will be written in one of these languages, right? So, you know, with Haskell, you can do pretty much anything you want to in Haskell. Same with C and Python, right? You can write any program in these programming languages. it's like, you know, if you consider the set of possible programs that's representable by these languages, those programs include, you know, the SQL compiler, the HTML compiler, and the R compiler. So, if you're working on something that's application specific, use an application specific programming language. It's normally worth your time to find one. And I've already talked at length about the difference between interpreted and compiled languages, so I won't harp on it too much. Generally speaking, interpreted languages can be easier to debug, although I would quibble with this point, to be honest with you. One of the reasons that interpreted languages became very popular back in the 90s, it was sort of first popularized by the Java virtual machine. The point of the Java virtual machine was that, you know, the clever brain boxes at Sun Microsystems could write an implementation of the Java virtual machine for all kinds of different specific computers, and then any Java program could be loaded into that specific instance of the Java virtual machine, and it would just execute, right? So it was like putting a layer between the hardware and the software so that the software could be run on any hardware because you designed different virtual machines. That was like the original idea with the Java interpreter. This was actually a really important, this was an important design decision at the time. It led to Java being an extremely popular language. Java is no longer entertains that level of popularity because this problem has been mostly solved by standardization. So the hardware is kind of caught up to it, and there's nothing at this point that Java does that's really like not done better by some other language. So Java is kind of falling out of favor, and you know, if you look on the internet for memes about Java dying, you'll never see the end of them. So. Anyway, I'm not saying that Java is a bad language. If there are any Java fans in the crowd, it's just been superseded. That's all. So, roughly speaking, we have three main categories of programming language. We have imperative or procedural languages, in which you write instructions to be executed. Object-oriented falls into this category, and this is what we'll be learning in this course. You also have functional or declarative languages. So these are more interested in you writing direct mathematics and the computer itself figuring out how to implement those mathematics. You are declaring what the answer should be rather than telling the computer how to calculate it. These tend to be higher level languages than the procedural languages. Like, languages in this category include C, C++, Java, Python. Languages in this category include Haskell. Logic languages are, they're kind of the odd duck. If you go on in computer science and take courses like 1DM3, you'll find lots and lots of material on formal logical specification and mathematical logic. Logic languages are, I would consider them a subcategory of declarative, to be honest with you. But they're, rather than express things in arithmetic mathematics, they attempt to express things in mathematical logic directly. So things like functions and relations and mappings and sets. It's like this is programming in like your regular garden variety elementary school math. This is programming in set theory, basically, is the idea. Anyway, any questions about that? Yes?
Can Latex be a part of logical?
LaTeX?
Yeah.
I wouldn't consider LaTeX a programming language.
Okay.
I mean, like, it's kind like it has aspects of it, but so for those of you who have never heard of LaTeX, which is probably most of you, LaTeX is a document generation system where you write up a bunch, like you write a document like it's code, and then you compile it, and it turns it into a PDF. If you are a computer scientist, it is expected, for example, that like any paper you submit for publication be written in LaTeX. It's also just a way better system than any other system, to be honest. So, like, I can show you some LaTeX source code if you want. These very slides are done in LaTeX. So this is what LaTeX looks like. Right? You can see this is all the text that's on all of these slides, right? This would get compiled into the slides itself in a manner that looks nice. But anyway, so LaTeX is an application-specific, like if I were to call it a programming language at all, application-specific, very, very, very application-specific, in the same way that HTML is very application-specific and not practically a programming language. There's no way to do a loop in LaTeX, as far as I'm aware, so that means it's not Turing complete, so it's not a programming language. Make sense? Yes?
Would you call R a programming language then?
Can you do loops in it?
I think you can. But
Then
it
yes.
doesn't happen.
Yeah. Basically, like, the way I consider it a real programming language is whether or not it's Turing complete. So in order for it to be Turing complete, you have to be able to do conditionals, you have to be able to do loops, and you have to be able to do a loop that doesn't terminate. If you have those three conditions, then I would consider it a real programming language. Make sense? Of course, you know, what the heck do I know? I just teach the course. So, differences in programming languages. Fortunately for everyone involved, once you know one programming language, it's much easier to transfer those skills to another programming language than to, like, if you learn Python here and you want to take 1xC3 next semester, or in the summer semester, which I totally recommend because it's an awesome course, which I teach, you're not starting from square one, right? Much of what you learn from Python would be applicable to C programming. For example, loops and conditionals and assignment statements all work in pretty much the same way in Python as in C. You can kind of think of Python as being C with a bunch of extra, like, goodies thrown in, right? So C is more basic, but Python has a bunch of extended stuff which we'll talk about. But, like, the core of Python is practically identical to the core of C. Yeah, and you can all, like, you can always tell whether a programming language is, like, one you should be interested in learning long term by whether or not its own compiler is written in the same language, right? So C's compiler is written in C. Haskell's compiler is written in Haskell. Python's compiler is written in C. So what does that tell you? Right? Anyway, so one of the most immediate difference that you'll see between programming languages is the notation or syntax which is used to compose the program. So last time I talked about how indentation is extremely important in Python programming because it tells you what's inside of what else, right? In C, you use curly braces for the same purpose. Same concept, slightly different way of writing it, right? Most languages use curly braces for this, by the way. You can also have, like, you know, a test for inequality will have slightly different symbols depending on what language you're using. You know, you could have, like, not x equals y, or x slash equals y, which is Haskell, or x bang equals y, which is C, you know. Python, Haskell, C. right? Each one of these expresses the same thought in but using slightly different syntax, right? So, safety. We don't really, it's not really useful to get into a great deal of type theory in this class. If you're interested in learning something about type theory, I recommend you take Computer Science 3 MI3, which is another class that I sometimes teach. Basically, some programming languages will check to make sure that you're not violating the type that's intended by the variable. Other languages will not. So, for example, in Python, if you try to add the numeric value 3 to a string, that's a type error, because they're not, addition doesn't make any sense when you're doing it on characters and a number, right? In C, it's a little bit more loose than that. Basically, in C, most things have a correct interpretation. You just your responsibility is to make sure that your program does what it's supposed to do. C is like programming without a safety net. So, support for large programs. So what we mean when we say support for large programs is how good are the mechanisms of abstraction, right? Some mechanisms of abstraction available to object-oriented languages, namely classes, are not available in lower-level languages like C. So C is not an object-oriented language. It is an imperative language because it does not have support for classes or object-oriented constructs. Python, Java, C++, all of these typical object-oriented languages do, right? Because they have these better mechanisms of abstraction, you can get the program to be larger before it collapses under its own weight. And that's not really a phenomenon in the language itself, because the computer doesn't care. What I mean by that is when a program reaches a certain size, it becomes impossible for a human to work with. You guys know what I'm talking about, right? So, if you write a program that's sufficiently large, basically, the larger the program is, the more different definitions for various functions and variables you have to hold in your head at the same time. There is a physical limit to the amount that a human being can have in their head at one point. So you need mechanisms for dividing the program into smaller parts that can be managed individually, right? Object-oriented programming is one such abstraction, and we're going to be studying it later on in this course. Another way in which programs differ is the degree to which they are supported by standard libraries. Generally speaking, you want a language with good libraries, and you don't want a language where you have to write all of the libraries yourself. Basically, everything that's not, everything that's not given to you by a library is something you have to write yourself, and you want to try to rely on, you want to stand on the shoulders of giants as much as possible when it comes to programming. In general, when you're actually doing actual code, like out in the wild, you want to use as much support from libraries as you can muster, because generally speaking, a lot more design effort goes into the library than it will into your program. So libraries are generally speaking fairly reliable, but again, it's foolish to place complete trust in any mortal being. So, given that libraries are written by mere mortals, it is foolish to trust them completely. Although they're usually pretty trustable. Also, portability to other platforms. This is not so much an issue anymore, but it used to be a big issue back in the 70s. So, and I know I'm running over the break. I'm just going to finish off these slides, and then we'll have our break, okay? So, Python. general purpose language, primarily imperative or procedural, can be object-oriented, can be functional. Basically, what they've done with Python is they've taken a C-like imperative language and given it like a light frosting, sugar, dusting of functional constructs to try to make the argument that it's a hip, modern, and cool language. Look at us. We can support lambdas. Look how cool we are. It's like, you don't! Not properly, anyway. Anyway, they consider themselves to be a multi-paradigm language somehow. It's a high-level language. It supports many mathematical data types, allowing programs to be abstract and easy to understand. This is the primary reason why it's taught as an introductory programming language, is because it's relatively easy to understand. I'm not convinced it's the best programming language to learn at first, because it, in my opinion, gives people bad habits by not being strict enough, but it is what it is. Python is a popular language and therefore has lots and lots and lots of standard libraries, which are useful. It's an interpreted language, compiles to an intermediate language, and then interprets that. This means that you can play around with Python on the fly very quickly. You can load up the Python interpreter and enter individual statements into it to see what they do. It's dynamically typed insofar as it's typed at all. Python uses a typing scheme known as duck typing. So if it looks like a duck and it acts like a duck and it quacks like a duck, then it's a duck, which is basically a way of saying, in Python, a thing is how you use it. So you declare a variable without a type in Python, and if you use it like it's a string, it's a string. Again, this is one of the ways in which Python is not sufficiently rigorous to, satisfy my personal desire for rigor. Compact and intuitive notation. White space is important, deadly important, and widely used in industry and academia. Basically, Python has established itself as a niche language for people who need to do some programming but aren't programmers, if that makes sense. Because anybody who strongly knows programming would use a more efficient language than Python. However, if you're a grad student in the science faculty, for example, and you have just a boatload of testing data that's come from some experiment or another, and you need to perform some operations over that data, you need to clean that data up before you give it to R or something like that. If you want to develop a machine learning model on it and stuff like that, Python is likely the language that you'll be using. And, I'm a little bit harsh on it because it makes a bunch of silly design decisions, in my personal opinion, but, I'm also how you want to say? I'm not necessarily the target audience, if that makes sense. Which is kind of strange because I'm a programmer and it's a programming language, but Anyway, so why is it called Python? It's actually been named after Monty Python because the guy who developed it liked Monty Python. You'll find a lot of that in computing, actually. People just naming things after random things, that is. So Python was started in 1989. It was created by Guido van Rossum of the Netherlands. It is an open language, so every year they have a Python conference where a bunch of Python people from all across the world gather and argue about why they shouldn't include switch cases. It's gone through a few iterations. Python 2 ended as of 2020, so everybody should be on Python 3. This shouldn't be a problem because pretty much every standard distribution of it now uses Python 3. So yeah, Python. Any questions? Okay. In that case, we will resume class at 10:40. Awesome. Thank you so much. So, moving swiftly on. Our next topic is expressions. So, what we mean when we say expression is roughly the same thing we mean when we speak about expressions in the algebraic sense. We're talking about a grouping of operators and things being operated on that can be executed to find some numeric results, or not necessarily a numeric result, but some single result which is derivable from a expression or equation, right? Now it's not an equation because we're not equating, right? But we are simplifying expressions, right? So, before we go anywhere, we need to talk about operators. So I'm going to perform a lot of these calculations inside of the Python interpreter directly. So inside of my my terminal here, I'm gonna maybe I kill the lights a little bit.
Just wait.
Better? Good. It's more of an issue when it's black on white right now. So this is a direct instance of the Python interpreter, which is running directly on my machine. At the 3 chevrons, I can enter Python code, valid Python code. Anything I enter here can be put inside of a Python file or an assignment file, right? It's just, you have to do it one line at a time, and you have to get those lines correct. So this is not a way to write a full program. But it can show us how certain expressions would be executed, right? So you can use Python as a calculator. You can do very simple things like 4 plus 5 is 9. 3 times 8 is 24. Multiplication is asterisk. Division is /. Make sense? So far, so good? Good. In Python, in contrast to other languages, exponentiation is 2 multiplication signs run together. So 2 to the power of 7, 2 to the power of 8, etc. Good. So, a little bit of terminology. The numbers that we are operating on, like 3 and 2.5, are objects. Python is an object-oriented language, so everything inside of it is an object. It's either an object or something that may become an object. In this case, we call these literal scalar objects. So an object is something that can be operated on. Again, everything in Python is an object. Scalar means that it's indivisible, not comprised of subcomponents. Another word for this is atomic, in the sense of atom, which, the Greeks believed that atoms were that matter was composed of some small indivisible portion, and then, the 19th century physicists thought that they had discovered the most indivisible thing, and then it turned out that was divisible, etc., etc. But the name atom stuck to, the elements of the periodic table. But anyway, so 3 and 2.5 do not divide any further than that. They are literals. That is to say, how you write them in the source code directly represents what they are or their value. You will hear me call these literals. I will not call it literal scalar object because scalar and object are assumed if it's a literal, basically. Although, you can also have literals that are not scalar, in particular, strings. Strings are collections of individual characters. They can be broken down because they are composed of characters, but the characters themselves are indivisible, right? So, these are literals. You operate on literals and variables. It's important to introduce, at this stage, a concept of data type. So data type affects how the number is represented at the binary level. It affects which operations the CPU can perform on the number. Generally speaking, you want to be careful mixing integers and floating point numbers. So integer, it basically follows its usage in common mathematics. It's any whole number, negative or positive, including 0, right? Floating point numbers represent the real numbers. So numbers which also contain a fractional component represented in the decimal system by, the decimal point and then a series of digits. Floating point numbers in computing cannot represent all real numbers. There's a good reason for this. Integers cannot represent all integers either. Both of these sets are infinite sets, right? There is an infinite number of integers and there is an infinite number of real numbers. Computers are finite machines. They cannot represent infinities, right? Although, arguably, you could have a special representation of infinity that is specially coded, but it is not possible to have a numeric representation that represents all of the numbers from 0 to that infinity. It's just not physically possible. In the same way, there is an infinite number of numbers between 0 and 1 in real arithmetic. Not all of these numbers can be represented by the computer because the computer is a finite machine. That being said, we have a reasonable approximation of it. We're going to be exploring the details of this approximation in probably week 3. We'll get to it. It's the numerical computation material. So, a floating point number is basically any number that has a decimal point in it. Okay? So, the difference between floating point and integer numbers comes out most strongly if you compare the two different types of division that you have available to you. So, in Python, you have both integer and floating point division. So if we take, for example, this example from earlier, 3 divided by 8, well, actually, you know what, let's do 8 divided by something like 7. There we go. I want a whole number component as well. Is this getting cut off? Is that okay? That's not quite. I'm gonna see here. There. So, if you use a single slash, this is floating point division. Despite the fact that the two numbers which enter into it are integers, the result will be a floating point number, even if those numbers divide evenly. Right? Despite the fact that these would result in an integer, the result is still a floating point number. Right? Contrast that with with integer division. If you use 2 slashes, that's integer division. You can see that the result is an integer. Whole floating point numbers are represented in Python by the fact that they'll say 0.0 after them, right? So, although 2 has representation both in floating point and in integer, it has both floating point and integer representations. These are, underneath the hood, in terms of binary, being represented very differently. So it's important to know the distinction. So the question then becomes, what happens if we use integer division and we have two numbers that don't divide evenly? We get only the whole number component, right? So, who here remembers long division? Integer division in this sense is half of the answer of a long division problem, right? Because when you do long division, you end up with, you know, the number remainder something, right? That remainder might be 0, but you get number remainder something. So this gives you the number, right? An operation known as modulus gives you the remainder. So the remainder of integer division is represented by the percent sign character. Now this is actually a pretty useful operation to be able to perform. You can turn a counter signal, that is a counter variable, a variable that is constantly just ticking up by 1 each second or something like that. You can turn that into periodic behavior by taking the modulus with respect to some number. So, you know, if you had like x, right, going like this, and you had like x mod y, you would get behavior that looks like where that is y minus 1. Make sense? Modulus. How many people have encountered that concept before? Yeah. So for a lot of you, this will be a new concept. It's a good one. It's good to practice. So yeah. Operators can be applied to objects to form expressions that yield other objects. So when we perform arithmetic, we take in two objects and an operator and produce a further object. You know, I should probably not be saying anything that wasn't intuitive. We recognize a distinction between binary operators and unary operators. Binary operators take two things and produce a further thing. Unary operators take one thing and produce a further thing. So, interesting little factoid, when you write -7 inside of the computer, you're not actually writing -7, you are writing +7 with negation as a unary operator applied to that +7. That's not really like useful information, but it's kind of interesting, I think. So, in Python, we have a type function which allows us to determine what the type is of any object. So you can see 27 is of class integer, 3.5 is of class float. Incidentally, this is how you call a function. It's called calling a function or invoking a function. So, for example, type of 8 is integer. Type of modulus is a syntax error. Type of type is class type. Fine. Any questions so far? Yes.
Is 2.0 and 2 like equal?
I'll show you. 2.0 equals 2. True. However, You should never, ever, 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 ever rely on equality comparison on floating point numbers for reasons that we'll get to when we talk about numerical computation. Okay? Basically, actually, you know what? I'll just show you right now. So this is a cautionary tale in floating point representations. Floating point representations sometimes are not exactly the number that they claim to be. They're often a very, very close approximation of the number that they claim to be. And this can actually affect your arithmetic. So if I have plus 0.1 plus 0.1, 4, 5, 6, 7, 8, 9, 10, 10. So if I take 0.1 and add it to itself 10 times, what is the expected result?
1.
1. You don't get 1. It turns out that 0.1 cannot be represented inside of floating point arithmetic with exact precision. The reasons for that, again, we'll discuss in a week or two when we talk about numerical computation, so hold your questions for that. But it's sufficient at this point to know each one of these guys has a tiny little error in it. If you perform repeated operations, you can sometimes get that little error to show itself. Now, 0.99999999999 is very, very, very close to 1. For all practical purposes, it is practically 1, right? However, if you want to see if something is exactly 1, using equality comparison, which is double equal sign, it is not equal to 1, right? You would expect, as a human being, you would expect this expression to be equal to 1. However, it is not. Even if I make this floating point representation. Make sense? Any questions? Yes?
How is type of class on its own?
Sorry, could you say that again?
How is type of class on its own?
How is type of class on its own? Because functions are also objects. Yeah. So when it says class, so the relationship between classes and objects. Objects are we call them instantiations, but an object is like a concrete example of a class. A class is like a template or a prototype that describes what an object is or what its properties are, what its operations are, right? So when we have 3, right, that is an object of type integer, right? The class that describes the number is integer. Does that make sense? Any other questions? Lots of good questions. Yes?
What is the modulus of 1 over 2?
So, are you saying 1 modulus 2? Or are you saying like 3 mod 1 over 2?
Yeah, the first one.
Okay. Yeah. So
But,
2 divides 1 0 times, remainder 1. So you get 1 as a result.
okay.
Yeah.
Okay.
Any other questions? These are excellent questions. I really want to encourage question asking because, for any question that you have, I guarantee at least 4 other people in the room are interested in the answer. So, yeah. Cool? Question?
So, what's the difference between type and class?
What's the difference between type and class?
Yeah.
Essentially, type is a function, right? It's an operation. You give it an input and it produces as its output the name of the class of the thing that you put into it. Does that make sense? All it's doing is showing you the name of the class that that object is an object of. Does that make sense?
So class is an object of.
No, classes aren't objects themselves. They describe how objects are created. It's like a template for an object, right? So, for example, and this is kind of this is jumping way ahead in the slide, way ahead in the course. But since you've asked the question, so the difference between classes and objects, right? Let's say that so here's an analogy, right? Let's imagine that your program is in the business of making submarines, right? The class is the blueprints for the construction of the submarine. The submarine itself is the object that has been built from that template, right? So if you want if you want like 10 submarines, you use one template to create all of those submarines, right? The template, like the blueprints, that's the class. The actual physical submarines that you build, those are the objects. Does that make sense? Good, cool. Yeah, all right. Any other questions? Good. So, we've gone through each one of these already, but you have addition, subtraction, multiplication, integer division, floating point division, remainder of integer division, and exponentiation. In general, Bedmus rules apply. If you want to orient the calculation in a different fashion, you use round braces. In programming, we use braces for all kinds of things. Braces are like the most important thing. Getting the wrong braces in an operation will completely screw up the operation and probably constitutes a syntax error. So, expression grouping occurs with round braces. As we saw previously, applying arguments to functions also uses round braces. So, in addition to the common mathematical functions, we have a large number of, like your extended set of math operations available from the math library. So if you import math, you can use logarithm, base 2 logarithm, you can use cosine, you can use arctan, you can use the definition of pi, you can use any of these mathematical operations that you have become familiar with over the course of your mathematical career so far, and probably a lot more besides. But yeah, trigonometry can be useful. So far, that's good insofar as it goes. We're going to now move, question?
What's the difference between operators and functions?
Largely academic. So, operators can be considered functions using infix notation. So, and that's a good question. There are some programming languages that allow you to mix the way that you represent things. And I'm going to talk a little bit about Haskell here. So, so in Python, if you have, 4 plus 6, right? The fact that the operator is occurring between the operands, that means that this is infix notation. So if you have an operand, 2 operands, if you have the operator in between, that's infix. If you have it before, that's prefix, and if you have it after, that's postfix, right? So in Haskell, you can easily convert any of these numeric functions to use prefix notation. All you would do is write plus for 6. And that is the same computation as this one, it's just using prefix notation. So if you were to like rearrange that very slightly in using pseudo code, if you do plus 4 comma 6, then this is the notation that's used for functions. Make sense? Any other questions? Yeah. So yeah, there's really like the only difference between function call and an operator usage is that operators are used so frequently that like we try to use slightly less clumsy ways of writing them so that we can write programs more fluidly. So, so let's talk about variables. I've talked about variables already, but let's just hammer the point home because it's extremely important. It's important that you should know what a variable is. So, in contrast to algebra, variables aren't actually variable. They do not have the property of variability. At least they can't represent multiple things at once. A variable in computer programming is some portion of memory which has been allocated for the usage of the program. Allocate is like the technical term used in computing for this. So, if you imagine your memory as like a great big cupboard with a bunch of doors on it, right? The first time your Python program uses a variable name, it takes whatever name you give it, let's say, X, for example. It finds a free cell in memory, labels it X, and it puts some value inside of it, optional. So, if you provide a value, then the variable is instantiated, right? That's taking this particular value and storing it in that little cubby hole. The next time you want to read whatever's in this cubby hole, you open the door and look, there's a 5 in it. That's how the memory works, roughly speaking. So it is possible in other languages to declare variables without giving it an initial value, in which case, whatever value was left behind in there by the last program that used the cell is what value it will have. Now, that might seem like a security vulnerability, but data is meaningless without context. Like one random cell in memory, even if it's like your bank password, is useless unless it's known that it's your bank password, right? So essentially, when a program shuts down, it doesn't typically clear its own memory. It just kind of releases it, and whatever process takes it next gets it randomly, and therefore it loses the context for what the data means, so the data doesn't mean anything, so it's fine to just overwrite it, right? Anyway, so yeah, you can also, I guess, think of these as numbers floating in a cloud, but I don't think that's as useful as thinking of it as a cupboard. But anyway, so variables are also objects. The type of the variable is the type of the thing stored in the variable in Python. In some languages, you declare the type of the variable up front, but in Python, it's basically you gather that information from whatever you assign to the variable. So in this case, base and height are integers because they are given integers, right? Area will be a float because this expression contains floating point division. So the return result of this expression will be a floating point number, which means that this guy here will have a floating point type. Does that make sense? Good. Excellent. So variable names can contain uppercase and lowercase digits, or uppercase and lowercase letters, digits, and the underscore character. So valid, like part of the interesting part of programming is designing variable names. So a valid variable name would be like, oh my god. Blackboard usage 0.03, and that can be interpreted as a percentage if you want, something like that. When designing programs and writing variable names, it is it's very important to pick names that are meaningful. There's kind of like a natural tendency to use, variable names like you would use in algebra, things like x, y, z, s, t, u, v, just letters, right? In fact, you'll see me do this often with the slides. However, when I write a program like that, I've got the slide to contextualize what that means, right? When you're just writing a program, the variable isn't contextualized in this manner. So it must provide its own context. The more descriptive your variable names are, A, the easier your program is to understand, both to other people and yourself, which both of those are important. It's totally a thing that you can write a program 3 weeks ago and completely forget everything about that program when you come back to it and you have to work on it again. And if your variable names are all nonsense, then you'll basically be starting from square one trying to reinterpret your entire program. Trust me, it's a problem. So that's number one. Using longer variable names that have more description will help you. We call it a form of self-documentation. On the other hand, however, it means that when you program, you have to type more characters. So it takes a bit longer to use longer variable names. Now, especially at the introductory level, as pretty much all of you will be, it's taking a bit longer to write is not, that's not the important part. The important part is being able to understand what you're doing. So, err on the side of longer variable names, please. Another thing that you have to keep in mind is that you can't use a variable name that is being used by Python for something else. So, for example, you can't have a variable named if, and you can't have a variable named while, because that would just be nonsense, right? It's like if is already used by if statements. You can't have a variable named at else, right? Make sense? Yeah. So, assignment. Assignment is the storage of a value in one of these cubby holes, right? We write it with just a plain equals sign. So, for example, if I were to say x is equal to 5, y is equal to 7, x plus y, or x plus 7 is 12, x plus y, there we go. You can perform math with variables in it. Right? So, on this line, I'm storing the value of 5 in the variable x. Here, I'm storing the value of 7 in variable y. Here, I am reading the values contained in x and y and performing addition over them. Here, I'm doing the same thing, but I'm multiplying y by 4 before adding it to x. Right? Math. Make sense, everybody? Everybody cool with that? Cool. So, you guys remember how we were talking about state last time? The values contained in each one of these cubby holes for each variable in your program constitutes the state of the program. When you trace the program, you are asking to see the intermediate values of this between the point of input and the point of output. Make sense? This isn't too bad yet, right? We're doing okay? Yeah. Don't worry, it gets harder. So, important point. Do not confuse assignment, which is written with one equal sign, with equality, which is written with two equal signs. Common mistake. Python will scream at you if you make it, so you don't have to worry too much about it because it just won't compile if you make that mistake. However, if you do this in C, it won't actually give you an error. It'll just do it, which means that you can have an if statement in which memory is being assigned during the execution of the condition, which is kind of strange and ridiculous. So just make sure, if you're comparing equality, if you're checking to see if A is equal to B, you're using double equals. Good. So, in Python, you can also do multiple assignment. That is to say, you can assign to multiple things on the same line of code. So this is actually an interesting example that I'd like to do. Let's say we had a scenario, and this scenario comes up quite a lot actually, when you're doing like algorithms and stuff. Let's say we have the value of x, the value of y, and we want to swap the values at those two locations, right? So, since you want to swap them, x is equal to y is equal to x. X then has the value of 7, and y also has the value of 7. It's very, 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 very important to understand that all of the operations that you enter into a computer are operated on sequentially. This one first, then that one. That means that this line overwrites the value in x that you wanted to store in y. So this is not the correct way to perform a swap. So, let's restore x to the value of 5, shall we? This is the way that you perform a swap. You must store the value in x in a temporary location. So, temp is equal to x is equal to y is equal to x. Therefore, x is 7 and y is what? Oh no. What did I do?
Y equals 10.
Y is 10? What? Oh, yeah, I didn't use temp. That's funny. Alright, let's try it again. Whoops, I got too enthused. I was getting carried away. So, temp is x is y is temp. Thank you. So, x is then 7 and y is 5. You require the use of this intermediate memory in order to make sure that the value that you want to write to y doesn't get overwritten by writing the value of y to x. This is implicit. This is done for you automatically by the multiple assignment in Python, but you should still know that this is what's happening underneath the hood. Good. So, yeah, I already talked about that. So, let's resume class at 11:30, shall we? Good. Thank you. So let's talk about comments. So, given that it's useful to name your variables useful things, it is also useful to be able to provide description of code in that code itself. To this purpose, pretty much every programming language provides the ability to quote-unquote comment the code. A comment is ideally some kind of explanation of what the hell is going on with the code, because code can be very difficult to understand if there's no explanation provided. From a grammatical perspective, what a comment is you provide some kind of symbol somewhere in the line, and then the rest of that line is not code, right? It's not part of the program. It's a way of designating characters in the file as being not a part of the program. Because they're not a part of the program, they don't have to follow the grammar of the programming language. They can follow the grammar of, whatever language it is that you speak. So, in Python, the character which is used to designate a comment is the octothorpe character. This is called octothorpe. I don't care if you think it's a hashtag, it's octothorpe. So, basically anything that you have after this character just doesn't get executed. Good source code includes lots of comments to help the reader understand the code. So, yes and no. There are good commenting practices and bad commenting practices. For example, it's bad commenting practice, if you're a real developer and not like a student learning the language, to explain how the language works inside of your source code, right? Anybody who knows the language should know what an if statement does, right? You don't need to say what an if statement does. That's assumed knowledge. You can over-comment in that way. However, for everybody in this room, because you're just starting off on this illustrious journey of programming with everybody else in the room, you should be erring on the side of more comments rather than fewer, right? It's better to provide too much description than not enough. But in general, the same principles which apply to good writing in general apply to good commenting. Don't waste the reader's time, right? There are paragraphs in books I'm sure that you've read that's like, oh my God, will this paragraph ever end? I get it already, right? You don't want people thinking that about your comments. Clarity, brevity, and wit. So, for example, in this particular calculation, we have a description of the calculation. We have a description of what the variable represents. We have a description of what this variable represents. And then we perform the calculation. Describing what a variable actually is or does or is meant to do is a pretty good use of time. Any questions? For those of you who are veteran programmers of other languages, Python does not directly support multi-line comments. In a language like C, or like practically any other language, you can denote a symbol as like the beginning of a long comment, and then have a terminating symbol at the end. Like in C, it's /* and then / is like anything inside this block is comment, which is very, very useful. In C, the single line comment is //. But in Python, like it has a thing called the doc string, which is like the rough equivalent of this in Python is 3 double quotation marks terminated by 3 double quotation marks, and then anything inside of this is comment. However, this is like, you can't use that everywhere. You can't, this is designating a block of text as being the documentation for a class or a function. So it's not really, like, we'll get to it. We'll get to how this is not quite the same thing as multi-line comments from other languages. But anyway, another very useful thing that you can use comments for is enabling or disabling code, right? If you've got a line of code that you'd like to see how the program runs without that being on, you just comment it out. And then you can run your program and it will ignore that statement. And if you want to re-enable it, all you do is delete the comment character and it's back in your program. Very quick, very easy. Programmer hacks. Haha. So, all right, good. So, we've talked about a few data types. We've talked about integers and we've talked about floating point numbers. Another, like, very essential, very basic data type that you will use quite a lot is the Boolean. B-O-O-L-E-A-N, Boolean. Booleans are true or false values. Quite simple. You can store Booleans in variables. Most of the time, however, you won't. There are a few uses of Boolean variables, but they're kind of like, most of the time if you need a Boolean, the Boolean will be the result of like an equality comparison or some other comparison operation. Booleans are the type of, they're a type that a lot of operations produce, but you don't store them a whole heck of a lot. Now that's, there are uses for it, like if you have a section of code and you'd like to see if you'd like your program to know if that code has been executed or not, you can set a flag. A flag is like a Boolean variable. You can set it to, say, false at the top. If that code executes, set it to true. And then at the end, after that if statement or whatever, you can read the state of the flag to determine whether or not that if statement executed, right? So that's one use of a Boolean variable called a flag. Cool? Any questions so far? Not too bad, right? Comparison operations yield, which compare integers and floats, yield Booleans. So, direct equality comparison, 2 equal signs. Less than or equal, is A less than or equal to B? Is A less than B? Is B greater than or equal to A? Is A greater than B? Is A not equal to B? All of these operations result in Booleans. So, for example, 4 is greater than 9. False. 4 is less than or equal to 9. True. 4 is equal to 9. False. 4 is not equal to 9. True. When we have control flow structures which are expecting a condition, what that actually means technically in terms of code is that they expect a Boolean result. So if you remember back to our flowcharts, we had a yes branch and a no branch. That's actually a true branch and a false branch. And I probably said true and false while I was presenting that because that's how basic it is. So, good? All good? Awesome. Question?
If we do type is equal to B, would it be Boolean?
Yes. Yeah, I'll show you. So, class Boolean. So this brings up an important point, so I'm glad you asked the question. this expression will be evaluated prior to the application of the result of that expression to the function, right? So order of operations is important. If you have a function that takes 3 plus 7 and 7 plus 9, the first thing that the computer will execute is this expression. It will calculate the value of this expression and essentially rewrite it. Right? Then it calculates the value of this expression and rewrites it so that the things being passed into the function are concrete values and not expressions. Right? Both of these intermediate steps will take place before the function itself is executed. Make sense? Good. And we're going to be talking about functions quite shortly as well. So, good. Once again, I'm going to harp on the difference between assignment and equality. Just don't mess them up, you know. Single equal sign is assignment, double equal sign is equality comparison. This is a memory operation. This produces a Boolean. Good. Questions? No? Good. So, let's talk about functions. So, a function. What is even a function? We've talked about functions, we've seen how to use functions, but we have no concept as of yet. What is a function even? In the early days of computation, they called them subroutines. A function is a set of programming statements which have been collected together and given a label so that they can be referred to by other parts of the program. So if I were to take something like, cosine, right? If you were to actually look into the library implementation of cosine, probably it's using a table to look up the value, right? That's just going to be more programming code. The same kind of programming code that's calling cosine. When you execute cosine, the program stops what it's doing in the main line of execution. It steps into the cosine function, executes it, calculates the result, brings that result back to the main execution, and inserts it into the function, or into the expression. So, for example, and I'm going to do this in Python tutor because it illustrates it a bit better, I think. No, I don't want that. No. Python tutor. Excellent. There we go. So, let's define a function, add 3. X, Y, Z. Return X plus Y plus Z. Well, you know what? Let's make it a little bit more beefy. Return plus equals Y. Return plus equals Z. Just so we can see the individual operations going on, right? So return, or not return, print 7 divided by, add 3 to 9 plus 8, 4. Right? Simple little program. Doesn't do anything particularly useful. So, first of all, where's my zapper? There we go. This is how you declare a function. You start off with the def keyboard keyword stands for define. You provide a name which you yourself design in the same way that you design variable names. You then decide what input variables you want. Right? How many inputs do you want? You give them names. You perform some set of programming operations, and you designate what you want the function to return as output here, using a return statement. So let's consider this expression. We have 7 divided by add 3, 2, 9 plus 8, and 4. So you can think of this as a series of rewrites, a series of expression simplifications, right? So the first expression simplification that will occur is this one right here. That, of course, is 17, so we rewrite replacing 9 plus 8 with 17, in the same way that we saw previously. Next, we have to find the return value of add 3 with these arguments so that that return value can be placed back into this expression. So when we do that, we open up an instance of that function running. This is called a stack frame, but you won't really learn why it's called that unless you take 1xc3 with me. So we open up a frame, which is kind of like a container for data, that relates to this particular calling of this function. We have the inputs 2, 17, and 4 provided inside of the frame. Our next operation, we create the new variable return, or ret, assign it the value of 2, execute the next statement, execute the next statement. Our eventual return value is 23. Now that we have a return value here, we can say 7 is this, the value of this expression is 7 divided by 23. Once this return operation occurs, the return value is decided. That gets substituted back into the original equation, and the value is printed because it's a print statement. Does that make sense? So, in a very real and literal way, when you call or invoke a function, you pause execution of this stage, enter into the function, execute all of the statements in the function, take the return value, substitute that back for the function call in the original expression. Does that make sense? Good. Any questions about that? Good. Excellent. Yeah, so functions, what functions really are, functions are a way of providing abstraction. It allows us to be able to label computing operations and then refer to many of them at once and in multiple places, right? So they're like the backbone of program writing. Like functions are really, really, really important. Like basically, once you guys get to the point where you're actually writing assignments, every single assignment question that you are being given by us during this course is written in the form of write a function that does this. The reason that we ask you to write a function that does this is so that we can take the code that you put inside of that function, we can execute it a bunch of times with a bunch of different inputs, find out if the output that your function produces is the one that we expect, and then grade you based on that. Right? That's essentially how the auto grading system works. Right? It's a little more complicated than that, obviously, but not much more complicated than that, which is kind of interesting. I'll explain to you how the auto grader works completely and fully once we've studied exception handling. So, syntax. I already went through it, but you declare a function with the def keyword, pick a name, pick a list of inputs, you write the body of the function, and return some return value. Incidentally, for practically all of the questions that you'll be writing on the assignments, this line is provided. The reason that this line is provided to you is, well, A, if the function has a name that we're not expecting, then we can't grade it, right? It's like, in order for the software to be able to pick out the function, the code that's in that function, it has to know the name of the function. So if you use a name other than the one provided, it just doesn't work, right? So please do not modify this line that's given. The same thing with inputs, right? If you change the number of inputs in the function, and we're calling your function expecting it to have 6 inputs, and it only has 4 because you rewrote it, that constitutes a syntax error, which will make the auto grader break, which means you don't get any marks, because fundamentally marks are deducted from the auto grader breaking. So, yeah. Yep. So, here's an example function, Pythagoras. So, everybody knows about Pythagoras, I hope. A squared plus b squared equals c squared. We have x and y, x squared plus y squared, and then we return z to the power of 0.5, which is Python shorthand for square root. Make sense? So, here's a question. What should this return? Anybody? Okay? Syntax error. Why?
Because there is no interface between string and parentheses.
Yes. There we go. So, in algebraic notation, this would be 3 multiplied by a plus b. In programming, this is a function call. So 3 is being used as a function name here. 3 is, however, not a function, so you get an error. You know, 3 times 4 plus 5, for example. Int object is not callable. It's not a function, you're using it like a function, so stop. That's what the compiler is saying to you right now. If you want that functionality, you have to actually use the operator explicitly that you want to use. Make sense? Good. So, this is kind of how this is like a good example of how programs are pretty picky about the way things are written, right? In programming, there's no shorthand, right? You don't get to write an equation faster by leaving out some of the operations because they're implicit. Everything must be explicit. Everything must be in its proper place. You must use the correct symbols for everything, and if you don't, the program doesn't work. With respect to this type of thing, programming is very, very, what's the word I'm looking for? It's intolerant of humans. Let's put it that way. Like human beings get along most of the time because you can kind of get away with loose thinking, you know? Like you don't have to have your concepts fully and properly defined to have a conversation with someone, you know? Which is a problem, actually, for humans, because, you know, most of the time when people are talking to people, they don't even know what the heck they're talking about. But in a computer, if you intend to actually program a computer, you must learn to write a program correctly and fully. And the computer will tell you that it's not correct and not correctly done if you try to run a program that isn't correctly done. There is no room for loose thinking in computing. You must know what every operation does, and you must know how to write them. That being said, it's acceptable to make syntax errors so long as you fix them before you submit your test. We will not be overly forgiving of syntax errors. If you submit an assignment question that has a bad syntax error, that means that the question is essentially complete nonsense. Do not expect any marks for it. Right? If you make a small syntax error, which makes you lose most of the marks, but the thing compiles and it's otherwise okay, we might forgive you for that and only apply a penalty to it and give you most of the marks for the first couple of assignments. By the time, except these are doubled up, so on the first assignment. By the time you get to the second assignment, if you're still making syntax errors and submitting them, do not expect any marks for it. Plain and simple. When you submit work, we expect you to have actually tried the program, right? If you have not actually tried the program, you will not know that there are syntax errors in it, right? However, if you have taken the most basic step to verify the integrity of the program before you submit it, that is, if you try to run the darn thing, you will find out that you've written nonsense. And it is our expectation, for example, on a test, that since you have the Python interpreter available to you to test to see if your program has any syntax errors, you will do so before submitting. Make sense? Good. Any questions? Yes?
So, my friend taught me that, I'm supposed to leave, spaces and whatever between, equal signs and, some other stuff to, for, ease of, reading and whatever. Will we get, doc marks for that?
No.
No? Okay.
Yeah, so in this class, you are graded exclusively on does it work as Python code. We're not really marking for what you would call form, right? Now, don't write ugly code, because it's good practice to not write ugly code. But, and in Python, certain elements of ugliness actually have semantic content, like the level of indentation actually is part of the program, And, in other languages, that's considered a stylistic thing. But Python encodes some stylistic things from other programming languages as actual program content. But no, we're not generally marking for stylistic issues. For example, you could not write a single comment the entire time you're here and still get 100% in the course if all of your programs are correct. The question is, how much more difficult is it for you to write programs that are correct if you're just not writing any comments? Right? Does that make sense? Any other questions? Yes, sir.
When's the first assignment?
It's next week. It's a bunch of questions, basically, like this type stuff and the first lecture from next week. That'll be the material that's covered on the first assignment. Make sense? Any other questions? Yes, sir.
So it doesn't really matter if we do it in 5 lines of code or 20 lines of code.
Oh yeah, I'm also not marking for efficiency. I have, I'll put an asterisk on that, there are certain instances where we do mark for efficiency, because it's like coming up, there are specific topics where we talk about, like, if you program in this particular way, it will take weeks to run your code, but if you program in that particular way, you can actually run it in less than a second. So occasionally we'll test, did you learn that? You know, did you pick up that technique? But in general, we do not mark for how long your code takes to execute, so long as it's, you know, reasonable. Nothing that you write in this class should take more than a couple of seconds. And the overwhelming majority should take practically no time at all. And like we're not marking you for like the number of lines of code that you write. And it's kind of like programming is a skill, right? When you start off, it's like any other skill. When you first start off programming, you're going to do a lot of stuff that's unnecessary, right? That you do because you don't quite understand what you're doing, but you know, it works, but you have all of this stuff that is, you know, not necessarily useful to the end task, right? The more experience you acquire in programming, the more you'll realize the things that you do that are redundant, and you just kind of snip them off as you develop as a coder. So it's like, you know, there are 10,000 beginners but only 3 masters, right? So over time, your code will more and more greatly resemble the code of other people who know what they're talking about, you know, because you'll have decided on the same types of optimizations as a lot of other people. That being said, there's still a very large, like, breadth of programming styles across different people. Most programmers are actually self-taught, so, or most programmers that are employed programming at least are self-taught, so, you know, there's, you know, less structure to the learning than you might expect when you actually get out into the field. But yeah, so my goal in this class is to give you the problem and give you the freedom to come to your own manner of finding the solution. The whole point is to build your problem-solving skills, right? This is, like, I have seen programming taught very differently a number of times. Particularly, you know, I'd say that the college system is a little bit more vulnerable to this way of going. It's like, there's a way of teaching people to program where it's like, here's a problem, this is the solution I expect you to memorize, you know, and then just do it. I think that is not a great way to learn how to code, right? If that's the way that you learn how to code, the only problems that you'll ever be able to solve are problems that you've seen before, right? Whereas, if you break the program down into its bare components, understand how those programs, how those components work, be able to break a problem down into its components, and solve the components of that problem with the language constructs that you've learned, you can program basically anything, right? So that's the intention with this course. I'm not going to give you a bunch of programming forms that I expect you to memorize. I'm not going to tell you, okay, at the beginning of your program, you have to initialize this variable, that variable, that variable, and that variable, right? That's not, yeah, you're chuckling, but yeah, trust me, the number of times I've seen it, you know? You know, like, this is a problem-solving course, you know? So if you're good at, like, math problems, word problems, problem-solving in general, this should be an enjoyable course. But yeah, it's basically like, if I give you a course where I just expect you to memorize a bunch of constructs and ways of doing things, and then you get out into the industry, you know, and you are presented with a problem you've never seen before, you know, I will have done you a disservice by your education. And because you guys are in the university system, rather than the college system, it's more likely that the types of problems that you'll see when you get out there are problems that have never been, like, that a solution does not exist for. Like, the issue with programming in general is that it's easy enough to repeat someone else's solution that, you know, it doesn't require a great degree of skill, right? Repeating someone else's solution to a problem is as easy as loading a library, right? However, to write your own solution, you know, that makes you valuable for a whole class of different applications that you know, if all you did was, you know how to use the API, that's, you know, yeah. I realize it's more difficult, and I'm expecting more of you, but I really feel like you need that if you're going to survive in the coming onslaught of automation and optimization, right? It's like the ability to solve a problem that's never been solved before is fundamentally like, that is like what the essence of science and engineering is, right? Well, engineering at least. Science is like, you know, the drawing of conclusions from observation, right? But engineering is the use of those observations in order to produce some beneficial effect, right? So, yeah. So anyway, I've perhaps waffled on about that long enough, but that should be a reasonable explanation of my philosophy for this course. Any questions?
Is it plagiarism if I copy code from my own GitHub?
I don't think so.
Okay. Well, will it get flagged though?
If it does, then just explain where it came from.
Okay.
Yeah. Like we're not unreasonable with the whole plagiarism thing, you know? Like we do listen to the argument that you make in defense of it. It's just, you know, the overwhelming majority of the time people have just copied straight off of Chegg, and it's clear as day, you know? But it'll be interesting. I'm not sure how much code, I'll put it to you this way. The more code that you already have in GitHub that's useful in this course, the more disappointed I'll be. Okay. Any other questions? Yes?
Sorry, I just want to know what like an assignment question would look like. Like,
Oh.
what would like you be asked to do?
Yeah, sure. We can take a look. Let's see, do I have any? So this is what Jupyter Notebook looks like, by the way. So this is like a slightly old version of assignment 1. So come on, load. Stupid machine. There we go. So this is something I would expect you to be able to do, like after having listened to this lecture, right? For example, create an implementation of the quadratic equation, right? Obviously, when you actually receive it, and this is an old version, you're not going to get the solutions block. You know, this is like the instructor's copy that has the solutions in it. I'm not particularly concerned because, you know, quadratic equation, it's like, has a very straightforward implementation. But at our level, it's like, can you do this in terms of code, right? That's where we start. After that, we gradually introduce more and more of the concepts that we study in class. Eventually, we're getting to the point where one of the bonus questions on one of the later assignments is implement checkers. So yeah, stuff like that. Make sense? Yeah, good. Now, that's a bonus question because it's a pretty long question. Most of the rest, it's mostly easier than that. Like, one of the object-oriented questions is like, write a bunch of functions that operate on vectors. Like you create a vector class and do like, dot product and a bunch of stuff like that, It's pretty highly mathematical just because that's the nature of the course. There's a certain amount of like data processing type stuff, given this set of data, extract this useful information. But yeah, that's like, that's the general flavor, if that makes sense. Any other questions? Okay, let's see if I can, let's see how far I can get here. Okay, so let's talk about tuples. So when you're programming with variables, it may occur that you want several variables with very slightly different names, right? You might be in a situation where, for example, close you. Yeah, I don't care. There we go. You might be in a situation where you want to say like x1 is equal to 3, x2 is equal to 5, x3 is equal to 7, x4 is equal to 9, etc., right? Now, you can encode things this way. This is totally possible, right? However, this is not optimal use of the computer. In particular, doing it this way makes it difficult to write a loop, because each of these, like, you would have to, the numbers here have been encoded in the names of the variables themselves. In theory, since they're numbers, it might be useful to do math with them, like jump ahead a couple of numbers or something like that, right? In order to deal with situations like this, which arise, we have linear data structures. So, a variable is a data structure that contains one thing. A linear data structure basically takes a whole bunch of variables, lines them up, gives them numbers, right? And gives them one name. So, and you saw me already use this last class. But actually, I'll do it here. So, if I say tuple is 1, 2, 3, 4, 5, 6, 7, 8, it's all stored in one variable name, and it can be accessed using square brace indexing notation. So the 0th element here is 1. The first element is 2. It's actually the second element. This is what's known as 0 indexing. The first element of the data structure is given index 0. There are very good reasons for this that you'll come to an awareness of if you take 1xc3 with me. Yes? How is this different from a list? Ha! That's a good question. Tuples are immutable, and we're going to explore the difference between those in this class. So the difference, basically, there are a few different types of these linear data structures that you can use, right? Most particularly, you have tuples and you also have lists. Most people will use lists for most purposes because they're slightly more convenient to work with. They have a few more operations available to them, and they're just like, there's more utility to a list than a tuple. However, tuples are faster. So that's why tuples are sometimes used. So a tuple is an immutable data structure. Once created, the values inside of it cannot be modified. Right? This means that it's slightly more efficient in memory because it doesn't require the same level of monitoring and moving around that a dynamic data structure like a list would, right? So because it's static and it just stays put in memory when you create it, it's easier to work with for the computer, so it's a little bit faster. But that also means that you can't modify the values in it while it exists. You can destroy it and create a new one with the modification, right? But you can't modify it directly. Any questions about any of that so far? Yes?
Is there a way you can make it into a list?
Sorry?
Can you make it into a list?
Oh yeah, there's conversion functions. Easy. Easy in Python anyway. If you want to turn a tuple into a list, you just call list on the tuple. If you want to turn a list into a tuple, you call tuple on the list. Nice and easy. Question?
You can't make that into an array, right?
Sorry, could you speak up?
Can we make it into an array?
No. Arrays are not a thing in Python. So essentially, an array is, it's kind of like the basic data structure that underlies both of these guys in the underlying C implementation of these things, right? So an array exists in C or C++, and many other languages use array, like the terminology array. In Python, you don't talk about arrays, you talk about either lists or tuples. Make sense? Any other questions? Yes?
Can we turn a tuple into a variable? Like, let's say I want to do a tuple is equals to then p dot is equals to 1 equals 9.
Yeah, okay, yeah, you can, so yes. So you're talking about here, right? Yeah, we can reassign that to another variable or even to the same variable. So like, for example, if you wanted L is equal to list tuple, bing, bang, boom. Yes. So these data structures are objects just like every other object. So you can assign them, which is another slight difference between how Python chooses to handle things and how other languages choose to handle things. A variable in Python can hold any object. These guys are objects, so you can assign these guys to a variable. You access the individual elements of it using square brace notation in both cases. Good so far? Good. These are really good questions, I have to say. So, I got all that, and I was still on the title slide of this section. So, tuples are lists of objects. Well, I mean, you know, a list is also a list of objects, but a tuple is a tuple of objects, but, you know. It's a linear arrangement of things, let's put it that way. The objects in the list do not have to be of the same type. Now, this is in stark contrast to something like a C array, because in a C array, everything has to be the same data type. Here, we're allowed to mix and match, right? Each one of these can be some object, including other data structures like other tuples, right? So, we've got 4, 7, the string potato, and true. This is a string, by the way. This is a collection of characters. We're going to be talking about those when we get there. We have a beefy section on that coming up. But yes, we can put any number of items we want into a tuple with a big ol' asterisk hanging off the end of that. You cannot exceed the size of the memory of your computer system. you know, or the memory that's made available to the Python process, which is not likely the entire memory of the computer system because you still have to run an operating system. But yeah, you can make these basically as large as you might want them to be, like millions of elements if you really want to, right? Tuples retain the ordering of the elements in them. This seems like a silly thing to say about tuples. It only makes sense when we contrast them to sets, which is another type, data type that we'll be talking about next week. The elements of a set have no ordering. Ordering doesn't make sense over them, which is true of mathematical sets. And you can assign tuples to variables. Questions? Good. Tuple operations. Providing a number in square braces retrieves the ith plus 1 element of the tuple. So again, 0 indexing. Concatenation. If you have two tuples and you wish to run them together, you can do that with the plus operator. So, for example, 1, 2, 3 plus 4, 5, 6 is 1, 2, 3, 4, 5, 6. Note that concatenating with something that's not actually a tuple is a type error, because you're trying to mix a tuple with an integer, and you need to only mix tuples with other tuples. Make sense? Good. We also have the length function, which we'll see a lot of. That returns the number of elements in the tuple. That's extremely useful. We also have, in Python, a default keyword for searching, which turns out to be very useful. If you want to know if some particular element is in the data structure, you use the in keyword. So, for example, with our data structure up here, L, or T, there we go. 3 in T, true. 13 in T, 13 in T, false. Right? Now, this kind of makes it seem pretty easy. There's actually quite a lot of code that goes into this tiny little 2-character operator, but, you know, that's high-level languages for you. It's compressing like a whole while loop into this guy, which is kind of, you know, interesting. It's like an inline, one-line while loop. But anyway, we'll get to that when we talk about searches. But yeah, that's very handy to be able to do in one line, as it turns out. So I think that's it for class today. The camera lasted all class, didn't it?
Yes,
awesome.
it did.
No subscriber-only section this time. Are there any questions before we head out? Yes.
Does the length function also start from 0?
No. So.
Like, what is the difference between the square brackets and this?
So length just counts the number of elements. So 1, 2, 3, 4, 5, 6, 7, 8. 8 elements.
Okay.
Right? The indexes of these elements, 0, 1, 2, 3, 4, 5, 6, 7.
Okay.
So all you're doing is providing like a mapping between the index number and the value that's actually stored at that location.
Okay.
Make sense?
Right.
Cool. Question at the back?
Can they be used in dictionaries?
Sorry, say again?
Can tuples be used in dictionaries?
Yes, tuples can be used as both the keys and the values of dictionaries. Because tuples are static, you know, equality is well defined over them, so you can use them as keys as well as values. But yeah. When we say this can be an object, in Python basically we mean any object, including classes. Or objects instantiated from classes, I should say. You seem like you know some Python already.
I know C++ and Java, but
Ah.
not too much Python.
Okay. Yeah, you'll probably find the first few assignments pretty easy then.
Hopefully, yeah.
Okay. All right, I think that's everything. Unless there are any further questions.